So again, what you pick up in the current voltage characteristic are multiple peaks, and the central resonance probes the states in the emitter. Okay? So, let me show you this again now with the current voltage characteristic that I've shown you before, but now with a rather complicated trace of resonances in energy and voltage space. So on the bottom left you see again energy versus voltage, and you see traced the relevant energies in this problem. So there's a central resonance C1 that is almost going down linearly, but no longer quite linearly, because we're solving a Poisson equation with charge. And since charge is involved in the emitter, and it's resisting, so to speak, the pull down of the Fermi sea on the bottom right, it doesn't move down quite linearly. You see the second state, C2, also roughly moving down linearly. Then shown is the Fermi level as flat, because it doesn't change. And you see in sort of yellowish orange the minimum conduction band edge, this point here, moving down in energy. It's also not moving quite linearly, because you have charge pileup here in the emitter, and it doesn't want to be pulled down. It's resisting the pull down, because it has enough supply from the emitter to pull up the charge. So then, here are the two new things in this realm, where we look at the emitter state E1 and the emitter state E2. And they barely move with energy, because they're confined in this triangular well, and the whole triangular well doesn't move a whole lot, and they are above the minimum conduction band edge here in the emitter. And there's one present even for very low biases. The second one is being found in the resonance finder for a little bit higher voltage. And they move very slowly. So, you can now see where if the central resonance C1 is lining up with the emitter resonance E2, you can go back up, that's where you find a high current flowing. Okay? So you pull the central resonance into the sea of electrons, into the Fermi level area. You start to conduct more and more, and current rises until you hit the resonance state. And once you're under the resonance state, you are not probing anymore a whole lot of electrons, or less electrons, and current drops. And then you're coupling to the emitter state E1 at a higher bias at 0.42 volt, and that's when another peak occurs. And you might ask, well, why is this peak not as large at 0.42 volts as it in 0.32 volts? Right? Should be the same, right? I mean, well, the answer is that these resonances here, E1 and E2, have different widths. They are supply functions that have widths associated with them, and they are important. Okay? And you're probing the spectrum in the emitter. So if you probe a broad spectrum, you can get a lot of charge. If you probe a very narrow spectrum, there's not a whole lot of charge in that energy spectrum. Okay? So those are the critical items now. And again, the central resonances probe the states in the emitter, and multiple peaks are visible. And now we're going to make this picture a little more messy. Now we're going to bring in these resonance widths. So on the bottom left you have the same thing, but now superimposed are these red lines that indicate the resonance widths of these states. So let's sort those out slowly. Let's look at the central resonance in the middle here. And what you have there is roughly a resonance that doesn't change in energy much. It doesn't get broader or narrower much. That's the central resonance that sees strong barriers that are slightly modulated. Let me see, yeah. Then you see the width of the central state C2, which is roughly a factor of 40 or 80 broader in energy than the ground state. So this is C2 up here. Now, you have an emitter state E1 here that comes into play early in voltage, and at first it's broader than the central resonance, okay? Or broader by the magnitude of an order and a half, so maybe a factor of 40 or so, okay? But what happens is you make this triangular well deeper and deeper, right? So you bind this resonance stronger and stronger. And there's a really big barrier here to the left, right? It can't go out to the left. It's almost like an infinite barrier. And then you have a non-resonant double barrier. That's also a pretty big barrier. That means this resonance gets narrower and narrower as you apply voltage. At some point it gets narrower than the central resonance, and it narrows by 1, 2, 3, 4, 4.5 orders of magnitude. And the second emitter bound state, E2, is always really loosely bound. It really doesn't move a whole lot into the well. So it's always broader than the central resonance. So if you're coupling here at this bias of 0.32, you couple the central state to the emitter state E2, you have a lot of current flowing because that's coupling to a broad resonance. Versus if you couple at 0.42, you couple the central resonance to E1, you're coupling to a very narrow resonance. Therefore the current is going to be smaller. Okay, so that's why the current here is larger than the current here. Okay? So now to the key messages in this section. So realistic RTDs have a non-uniform doping profile that keeps dopants away from the central RTD to avoid ionized impurity scattering. So there's a technical reason why you introduce these low doping spacers. This non-uniform doping profile results in a non-uniform electrostatic potential profile above the Fermi levels in high contact regions. Right? It basically pushes the whole RTD way out of the energy spectrum at first. An applied bias causes a potential drop not only in the central RTD region, but also in parts of the emitter. That potential drops in the emitter and it creates a triangular well. And that triangular well binds quantum mechanical states that interact with the central RTD. So you have a coupled resonator problem. You have a resonator in the center that you really wanted to create, and you have an emitter resonance that you kind of didn't want to create, but you have it. And the quasi-bond emitter states resonances vary exponentially with the applied bias and become extremely narrow. Okay? All right, so with that, Giuseppe, you had a question.
Okay, yeah. Let me just try to remember. In the simulation, basically you assume that your reservoir was up to the first value, right?
Yeah.
So actually the emitter bound state was in the reservoir and was occupied with equilibrium.
Right. That's right. That's exactly right. And we'll highlight this in the next presentation, because that's going to be really important. And the reason why I'm trying to have questions at the end, we have to edit out. Boy, that's you missed the first lecture. Come on. All right. Are there any questions? Am I still going at the right pace, or is this getting too fast? Because now I'm really adding more and more facets to this, right? And if you feel like going too fast, you got to let me know, right? Feel free to let me know. This is for you guys, not for me.